Hi there people, welcome back. Gary Simmons here for the Game Institute, and here's another video release from our Dead Earth game development series. Now in previous videos we've learned how we can take the static objects in our scene and compile a navigation mesh from them, and we've seen how the agent can use this navigation mesh to plot paths because it describes all of the traversable areas in our scene. But how do we handle dynamic objects whose positions are ever changing at runtime? We might have a stack of crates, for example, which can be pushed over by the player, a wall that crumbles into a pile of debris, or something much more simple and rudimentary, doors that open and close. Because these were not compiled into the nav mesh, the agent will not know they exist using just the standard pathfinding algorithm. So instead, Unity also has an additional dynamic object avoidance system built in. Now, we've seen Unity essentially using this already. You will remember that when we placed multiple copies of our agent in the scene, they all were able to avoid each other. So in a way, we can think of the agent itself as being a form of navigation obstacle. But Unity has a special component called the nav mesh obstacle component. It's just a bounding volume, either a capsule or a cube, that we can wrap around one of our dynamic objects, and the agents will be aware of that bounding volume and will try to avoid it and steer around it. So let's have a look in this lesson at how we can use the nav mesh obstacle component. Now, before continuing, do remember that in the last lesson I had done a few things. For example, I had put these waypoints on top of these buildings here, and that was because we wanted to demonstrate manual off mesh links. So I want to put these waypoints back in their original rooms, okay? And if I select the waypoint network 1 in the hierarchy, you'll remember that for our demonstration we also had deleted the remaining 4 waypoints from the waypoint network. So let's set that waypoint count back to 6 again and just hook up those connections again for waypoints 3 through 6. And finally, we'll put our agent back in the initial room that it used to be in. Roughly where it's going to start. There you go. Let me just press play a minute, check it's all working. Oh yes. In order to have one of our dynamic game objects recognized by the navigation system such that our agents try to avoid and steer around it, we have to add a special component to it called the nav mesh obstacle component. This is essentially a bounding volume, much like we use colliders to represent more complex objects to the physics system. NavMesh obstacles describe objects to the navigation system as either bounding capsules or bounding cubes. We've also seen that the agents themselves are represented in the simulation as nothing more than bounding cylinders. So let's create a new game object now, put it in the scene, and see what happens when our agent approaches it. So I'm going to go to the game object menu, I'm going to choose 3D object, and I'm going to create a cube. And with this cube I'm going to make it a little bit bigger. It's actually width I want. And what I'm going to do is I'm going to block off this passageway here. There you go. Okay, so if I press play now, I think that's the way that our agent is going to try and go. Yes, look what happens. The agent passes straight through the cube. See it again? Even though our cube has a box collider on it, the navigation system pays no attention whatsoever to colliders. They are part of the physics system. They're not linked to the navigation simulation in any way. So what I'm going to do is I'm actually going to remove the box collider from this cube because it isn't doing anything. Instead, we need to add a nav mesh obstacle component. So let's do that now by selecting the cube object and in its inspector clicking the add component button. Type nav and then choose nav mesh obstacle. You should see the nav mesh obstacle component now added to the object. The first property is the shape of the bounding volume that's being used to represent this object. Now in this particular case our object is a cube, so it's chosen intelligently to use a box volume and resized it correctly to bound that volume. But we could change that to a capsule volume if we wanted to, and change the height, the radius and the center point. I'm going to choose the box volume because that is a perfectly tight fit around our cube. So now we have a nav mesh obstacle in our scene. To the navigation system, this is much like a collider. The agent will not be able to walk through any item that has a nav mesh obstacle on it. So we might think when looking at this that our agent would notice that this path is blocked and would choose to walk around to the room the other way, going off round to the right. However, that's not what's going to happen. As you can see, our nav mesh obstacle has correctly stopped the agent from walking through, much like a collider would. But it doesn't cause the agent to repath to that destination. And that's because this obstacle is not part of the nav mesh at all. Therefore, it isn't factored into the pathfinding algorithm, which uses the nav mesh. If we move this object around, we can see that the agent will just try to push into it to get to its route, but it won't change its path. By moving the obstacle, we can also see that pushes the agent back as well. And we can see that if we move the obstacle out the way, the agent goes happily about its path. Now, up until very recently, Unity 5 I think, or it might have been late in the 4.x cycle, I do believe that this was the only type of nav mesh obstacle. Now this obviously causes a bit of a problem for doors. Now, doors open and close. Now when a door is closed, we would want our agent to intelligently recognize that, and in the case of our zombies, not just walk up to the door and just stand there with its head against the door, just walking into it. We would expect it to stop and find another route into that room if one exists. Fortunately, with Unity 5 we can do that. It now has this new option called carve. When we select this, the bounding volume will actually be carved out of the nav mesh at runtime. If you look on the right hand side of the cube here, you can see that the cube is indeed being carved out of the nav mesh. Now of course, as soon as it's carved out of the nav mesh, the path will no longer be valid and our agent will try to reset its destination. So let's have a look and see if it correctly now branches off to the right now that we've carved that obstacle into the nav mesh, and you can see it has. I'm now going to do that again, but this time when we press play I'm going to very quickly move it out of the way. As you can see in this particular case, the nav agent was able to ascertain that there was enough of a gap to fit between the nav mesh obstacle. The point I'm trying to show you there is really just that this carving is happening dynamically. Okay, so that's pretty cool. However, if I go back to the inspector of the nav mesh obstacle again, you can see that by default when we select the carve, these other options pop up, and by default carve on stationary is set to true. Now because carving into the nav mesh is a very expensive process to do at runtime, we don't really want to do it every frame. If I was to untick that carve only stationary tick box, our nav mesh would be getting carved in every single frame, like so. We can see that happening in front of our eyes. However, by setting carve only when stationary, Unity will use the movement thresholds and the time thresholds to ascertain if the object has stopped moving and for how long a time it stopped moving, and when it considers it to be stationary will only then carve it into the nav mesh. And this is a really good thing to do for things like doors, for example. If we have a door that was sliding open over a 2-second duration, we wouldn't want at 60 frames per second or whatever for that door to be repeatedly carving into the nav mesh. There could be loads of dynamic obstacles all trying to do the same thing. That would be very costly. A nice middle ground is to say that when the door is closed, it will be carved into the nav mesh. But as soon as the door starts opening, we basically stop carving it and we treat it like a regular dynamic object. Then when it's fully open, we recarve it again. I mean, not in this particular example, but you understand what I mean. So when the door is moving, we will have a situation where the agent will still be trying to get in through that door. It won't repath. So if you imagine in our game, we've got a zombie chasing us. We run into a door that is open. The zombie is tight on our heels, and just as it's about to walk through the door begins to slide shut. Now while the door is sliding, you'll still see the zombie kind of running up to the door, trying to get into the door, pushing against the door. But the minute that door locks shut, it will be carved into the nav mesh. The nav agent's path will become out of date or stale, and it will repath to the destination again. And this time it will say, hey, I can't get to the player, or at least I can't get to the player that way. And it will hopefully find another route if one exists, and if one doesn't exist, then it will just select a waypoint and go off patrolling as normal. So I think the best way to demonstrate this is to actually create a simple door in our level that animates. So I'm going to delete our cube from the scene, and I think the door we'll create will actually bridge this gap here. Okay, so I know it's a bit boring, but we're going to make this door out of yet another cube. So let's go to the Game Object menu, 3D Object, and select Cube. Then I'm going to left click on the cube and wait in the hierarchy view. I'm going to rename this door. Then I'm going to press Control and Shift, and then when we move our little door cube, it's going to snap to the floor, and that just helps us get it roughly where we want it. Now the door is actually facing away from us at the moment. You can see the Z-axis facing away, so I'm going to flip that 180 degrees using the inspector. And then what I'm going to do is I'm going to scale the X so it fully bridges the gap. I'm going to make it a little bit thinner because that door is too thick. It doesn't have to be exact, obviously. We're just looking for something that is roughly right. All we need it to really do is just fill the gap. That should do nicely. And we've got a box collider on this at the moment. We don't need that. That's ignored by the navigation system. For the record, it doesn't hurt to have colliders on navigation objects. They're just not used by the navigation system, but in Dead Earth there's plenty of cases where we have items that have colliders on for physics-based reasons and have nav obstacles on for navigation reasons, so that's fine. Okay, so now I'm going to add a component. I'm going to add the nav mesh object component. So do you see what I did then? Click the add component button, selected nav mesh obstacle. Now at the moment this isn't set to be a carving obstacle, and that's fine. I'm going to leave it like that for now. So when we first execute this sliding door, when it's closed it's going to act more like a repeller. It won't be causing the agent to repath. It will just block the agent from going in there. And then we can play around with the different modes. Now quite often, if you see Unity tutorials, they generally do sliding doors using like an animation state machine. Now maybe it's just because I'm an old school coder, but that just seems more long-winded than just writing a simple script that does the sliding for you. Now don't worry, we're going to be covering animation state machines in a lot of detail in the upcoming videos. Our whole first-person arms and weapon system uses it, and we're going to be using it as well for all of the animations of our zombie characters. But for a simple door like this, rather than just create 3 separate animations and then a state machine and do all that, no, just easier to write a script. Okay, so the way that this script is going to work is we're going to take some liberties because this isn't going to be like a final door script. This is just going to be a simple test script. So the script is going to assume that the door starts closed, and then it's going to record the position at startup, and that's going to be the closed position. And then what we'll do is we'll specify some offset in the inspector of our script that will be like a slide distance that will just describe how much we want this door to slide along its right vector when it's open. We'll do that calculation, and then we'll have both an open position and a closed position. And then when the user presses the spacebar, we will literally just, if it's closed, we will interpolate over some duration that we specify that it moves between the open position and the closed position. And then obviously if we press the spacebar and it's open, it will interpolate between the open position and the closed position. And because we've got a nav obstacle on this already, obviously when it's open, the agent will be able to walk through. When it's closed, well, obviously the nav obstacle moves with the door game object, so it will seal the gap. Now I'm going to create this new script in our navigation example folder, because like I said, this isn't going to be any permanent script that we use in Dead Earth. We'll do something a little more complicated later on once we've got our proper level geometry in. So right click in the project area, choose create, new C# script, and I'm going to just call this the sliding door demo behavior. Okay, and I'm going to drag that onto our door game object so it's ready to go, and then I'm going to open it up in MonoDevelop. Now I know one of the first things I usually do is delete this start and update function, but we actually need them. in this script, so I'm going to leave them alone. But what I am going to do is I'm going to create a public enum called door state, and the door will either be open, animating, or closed. And obviously if it's in the process of being animated, then it just means that we don't try and open and close it. It's essentially our way of saying the door is currently either sliding open or sliding closed. Therefore, when we're animating, ignore any taps on the spacebar to launch another animation of the door. The actual sliding itself we will do in a coroutine. So we're going to need some public members that we can set in the inspector. I'm going to have a float called sliding distance. We'll set that by default to say 3.5 meters. You just go back and look at the inspector to make sure. So it's at -17. Take it up. Yeah, to 22. Yeah, about that. Let's try 4. Then we know it will definitely get out of the way. And then we'll have another float called duration, and this is where we can set how long we wish the animation to take. Allows us to control the speed of the animation. So if we set this to 2, we're saying we want the door to go from the open to closed state, or vice versa, over 2 seconds. Although 2 seconds is probably a little long. I'll go for 1.5. And as we're going to be doing an interpolation, I think what we'll also do is we'll do another animation curve to shape that curve so it's more like a ease in, ease out animation. Much like we did in the last lesson when we used an animation curve to perform a parabolic jump of our agent between 2 off-mesh links. And I'll call this animation curve jump curve. Then we have to allocate it. New animation curve, like so. Now we're going to need some private members as well. So the first thing I like to do is I like to cache the transform of the game object. Now this used to be vital for performance in early versions of Unity, but in Unity 5 the transform property is already cached, so it's not so important, but I like to do it anyway. It at least saves a function call. So I'm going to say transform equals null. We'll grab a reference to that in the start function in a minute. So like I said, what we're going to do is we're going to record 2 positions that we're going to slide between. The closed position, which is the position our game object starts off in. And then we're going to calculate the end position, which is going to be the start position plus that slide distance multiplied by the right vector. So we're basically just creating a vector that is offset 3.5 meters to the right of our starting position. So once we've got those 2 positions cached, it becomes really easy just to do a vector lerp between the 2. And these don't need to be public. We're going to calculate them in the start function. So we'll have a vector 3 called openPos. We'll just set that to vector 3, 0 at the start. And we'll have another vector 3 and we'll call that closedPos. And we'll set that to 0 by default as well. And finally, we need a variable of type doorState, so that we can record what our door state is at all times. So we know it's going to start closed, so we'll say door state, and we'll just call our variable door state as well with an underscore. So we'll set the door state to closed to begin with, like so. So that's all the properties we need. Okay, so first thing we're going to do in our start function is cache a reference to the transform. That's easy to do because MonoBehavior has this transform property. So we can just say transform and fetch it that way. We don't have to do get component like we do with many of the other components. And then we need to calculate the closed position. Now that's pretty easy because our door actually starts off in the closed position. That's one of the restraints that we're putting on this script. So we just have to grab the position that it's currently at when our start function is called. So we can just do closedPos equals transform.position, like so. And then openPos we need to calculate, which is just going to be basically closedPos, and then we add on to closedPos slide distance multiplied by our right vector. So we're basically creating a vector that is pointing to the right of us, which if we look at our door is where this yellow arrow is pointing. But it's going to be 4 units long. So then if we have this vector that's 4 units long and we add that to our current position vector at startup, it's going to describe a position over here somewhere. So sounds like a plan. So we'll do open position equals closedPos plus transform.right, the right vector of our current transform, multiplied by our sliding distance. And that is our open position now calculated. Okay, so before we move into the update function, I'm just going to create the shell of the function that's going to do the actual animation, and that's going to be a coroutine, so it needs to return type IEnumerator, and I'm going to call it animate door. And it's going to take a single parameter which is going to describe the door state that we wish to move to. So if we're currently in the open state, when we press the spacebar, we're going to call this function and we're going to pass in door state closed. And if we're in the closed state, we'll pass door state open. So we're basically describing what the state of the door will be when this coroutine has finished doing its funky business. So it needs to take a parameter of type door state, and we'll just call this new state. And now I'm going to jump back up into the update function, and this is just going to be a single conditional in here, which is just going to check that the door isn't animating and that the spacebar has been pressed. And if the spacebar has been pressed and we're not currently animating, then we're going to start this coroutine. So if input.getKey down, remember getKey down will only be true for the frame in which the key is pressed. It's not the same as getKey, which will always return true while the key is being depressed. So getKey down is fine. We just want to register the key being hit once. And I'm going to pass in key code space for spacebar. So if the spacebar has been pressed in this update and our door state is not currently in the door state animating state, then it means this is a valid request to perform some animation on the door. Now we haven't seen it yet, but when we implement the animate door function, the first thing it's going to do is set door state to animating, and then just before it ends it's going to set it back to whatever new state is. So while the animation is happening, this clause will never be executed to animate the door again, because door state will be set to door state animating. But we'll see that in a minute. So assuming the spacebar has been pressed and we're not already animating, we're going to start our coroutine. And of course it's called animate door, like so. And as a parameter we need to send it the door state we wish to move to. So if we're in an open state, we need to send door state closed. And if we're in a closed state, we need to send door state open. So if door state equals door state open, then send in door state closed, otherwise send in door state open. So as you can see, that's just that shorthand way of doing a kind of if else statement. We're basically saying if door state is open, then this part of the argument after the question mark gets passed in. Otherwise the bit after the colon gets passed in. So if it's open, pass closed, otherwise pass open. And inside the animate door function, the first thing we're going to do is we're going to set our door state to door state animating, which means that in all future updates, until this function returns, this can never be called again. We can never try to reanimate a door that's already animating. So next we need a float variable to keep track of time, because this animation has to happen over a period specified by our duration member, which we'll set in the inspector. And this is going to be set to 0 at first, and we're just going to use this to count up to the duration. And now what we need to know is we need to know what the start position and the end positions are going to be for the interpolation. Now we know the open position and the closed position, but what we don't know is what the start and end position of the interpolation is, because that changes depending on whether the door is currently open or closed. So if the door is open, we want the start position to be the open position and the end position to be the closed position, and vice versa. So we'll just create two vector3 variables here. The first one I'm going to call start pos, and we're going to use that shorthand if else sort of syntax here, and we're going to say if the new state, remember new state is the state we wish to move to, which has been passed into the function, equals door state.open. In other words, if we wish to move into the open state, it means we're obviously in the closed state, so our start position needs to be the closed position. Otherwise it needs to be the open position. And then we're going to do something very similar for the ending position. I'm going to call it end pos, and we're going to say if new state equals door state open. So if the new state we wish to move to once again is the open position, then that means the ending position of the animation must be the open position, because that's the position we wish to move to. Otherwise the end position must be the closed position. If you're not used to doing this kind of shorthand if else sort of syntax, it's pretty cool. Oops, I put vector 3 there, vector 2 sorry, instead of vector 3. So we now know the start and ending positions that we wish to interpolate to and from. So let's start our while loop now. which is going to keep iterating until our time counter exceeds our duration. And the first thing we're going to do inside the loop is we're going to calculate that t value, that normalized time that we can send into the vector3 lerp function. So just like we did in the last lesson, t equals time over duration. I don't want to do a load of validation here, so it's pretty important that you don't set duration to 0 or we'll get a divide by 0 here, okay? So just make sure duration is non-zero. So we now have our time represented with respect to duration as a 0 to 1 value. So now we can set the position of this doors transform by doing transform position equals vector3.lerp start pos, end pos, and send in the t value. We also wanted to use an animation curve to do an ease in and ease out. So what we're going to do instead is, instead of just sending t in, we're actually going to evaluate t on our jump curve. So we'll say jump curve, evaluate t. And you'll see in a minute when we create an ease in, ease out curve that this just stops it being a straight linear movement. So it will start slowly, it will pick up speed, and then as we approach the ending position, it will begin to slow down again. So it just gives a much more organic animation. So next thing we want to do is we want to make sure that we update our time with the time that has actually passed by adding on time.delta time. And then, very important, as this is a coroutine, we need to yield null so that we only do one iteration of the while loop per frame, so we don't tie up the execution of our program. And then what I'm going to do outside the while loop is, it is possible with floating point inaccuracies and things like that, that we don't know what the frame rate is. So when time actually exceeds duration, it could be some way after duration, and this could affect the final position a little bit. So I just want to make sure, because I'm not sure whether the lerp is actually clamped. I don't think it is. So assuming it's not, I'm just going to do a little bit of a paranoia or sanity check here. And once we get outside the while loop, we know the door should have moved to the end position. So I'm just going to forcefully set it to the end position just to make sure. So we're going to say transform.position equals end pos, like so. Now at this point, while all of this has been going on, so say for example we set our duration to 5 seconds, this function would be iterating in this while loop for 5 seconds, and once that 5 seconds was complete, we would leave the while loop. But while this function has been executing over that period of time, door state has been set to door state animating. So we just need to make sure that at the very end of the function we set it to the state that it's supposed to be in, which is the new state that we passed in, and that way it unlocks the conditional up here again, which means that our application will once again become responsive to the spacebar being pressed. So we're going to finally say door state equals new state. I'm going to save that off, and then I'm going to flick back to the editor and wait for the barrage of errors. Hey, no errors. I'm actually getting quite good at this. Okay, so before we run it, we have just one thing that we have to do, and we have to set that jump curve. Notice in the inspector we've got the sliding distance and duration parameters. I'm going to leave those as they are because they might work out alright. I don't know till I test it. And we've also got this animation curve called jump curve. Normally, if we didn't use this animation curve, if we just did a straight lerp, then what we would essentially have is a straight linear graph. So for whatever the t value was, say the t value was 0.5, if we evaluated that on the curve, we would just get back 0.5. But down the bottom here, in the animation curve window, you'll notice that there are a few presets, and if you click this last preset, what you get here is an in-out curve, and you can see the shape of it. It means that when we're at 0.10, for example, on our t value, when we feed that in, we get, oh, it doesn't actually tell you, but a much lesser value. So the point being is that by the time we get to the midway section, it's kind of linear, but at the start and at the end, it's not linear. It sort of starts off slowly and it slows down as well. So with that ease in, ease out curve set, I'm going to run this puppy, and then I'm going to press the space bar, making sure I click in the game view first so I get keyboard focus, and I'm just going to hope this works. Oh wowzers, it works. Okay, so where's our agent? There he is, he's coming around. You've got to wait for him. And just as he gets to this door, I'm going to close it. Now as you can see, because this isn't a carve enabled object, he's just queuing by the door. He's waiting for something to happen, but he's not repathing. And if I open the door again, hey look, he can get in. Cool stuff. And you can see that while it's animating, if I press the spacebar, it doesn't react, because we've kind of locked out the spacebar in the coroutine using this animating intermediate door state. Okay, so that's pretty cool. So I suppose the next thing to try is to see what happens when we set this as a carving object. And actually, just for this demonstration, I'm not going to say just carve when stationary. I'm just going to have it continually carving. And that way we'll be able to see it working in the scene view if I choose the navigation window. So let's press play again. And we can clearly see that our nav mesh has been broken. I'm going to open it. And you can see the nav mesh now bridges the gap. Our door is no longer being carved into it. So hopefully our nav agent should choose to come here. But if I close the door, oh look, first of all, it kind of stopped it, and then it repathed. Pretty cool, huh? And if I open the door again, I think it's going to come out of here next. Yes. Didn't close the door in time that time, but you can see that it's working. Just try that one more time. Obviously, if we start and the door is closed to begin with, then our agent will never try to come through this door. And just to check it, works, we'll set it to carve only on stationary. So when we see our agent coming, we'll close the door. Now it doesn't repath yet. It waited a while before it repathed, and that was because only when the door wasn't moving anymore. There you go. Only when the door wasn't moving anymore for, I think, 0.1 of a second we've got it set to. No, sorry, half a second. See if you look time to stationary. Then it actually carves it into the nav mesh. And we should be able to see that. You can see when it's moving, don't worry about the agent for now, just look at the nav mesh. While the door is moving, it's not carving. So it's just being used as a standard sort of repeller of agents. But as soon as it stops, we then see the carve happening. There you go. And I think that's probably the best way to use these things. Now, as you can see then, I don't know whether you caught that in the top window, the agent was heading off down this way, and then when I opened the door, it changed its mind and automatically repathed through the new opening. So that's pretty much dynamic obstacles for you. Okay, so as you would expect, all of these properties of the nav mesh obstacle are also available via scripting. So if we wanted, we could just turn these properties on and off, and we could set the movement threshold and the time delay threshold via scripting. And if you look in the Unity documentation under nav mesh obstacle, there you go. You can see all of those properties are there. So we have the carving boolean, which we can just set to true or set to false via code, and that's something that we can do and we may do. And of course, there's other ways that you can handle doors. Like you could, for example, instead of using a nav mesh obstacle, you could actually use an off mesh link, which is only activated when the door is open. So the door itself wouldn't have any nav mesh obstacle on it, but it would be baked shut, I guess, so that there would be a break in the nav mesh. And then at runtime, you could have some script on your door such that when it opened, it then enabled a nav mesh link which connected those two floor pieces together. Honestly, I don't really know yet which one's best. I've got doors working in Dead Earth at the moment, but I've by no means settled on the definitive system that I'm using. So I will keep you posted on that. So this has been a shorter lesson, thank God, and it wraps up our navigation and pathfinding tutorials. I bet you're glad to hear that. I certainly am. So thanks for listening, guys. We pretty much know everything there is to know about Unity's navigation system now, and it's going to be fun later on down the line after we've covered animation and animating state machines, seeing how we get this to work together with animated characters, where we wish the character's propulsion to be controlled from the root motion in the animation and not the actual nav agent. So cool times ahead. Thanks for listening. Bye now.